In this lesson, we continue with trigonometric integrals, but in this video, we focus on the integrals of the form of tangent to some power, secant to some power, uh, x dx. And in this lesson, we uh, study two cases of integrals like this. There are more cases, but in this lesson, we only focus on two cases of these integrals. Before mentioning those two cases, let me make two reminders. One is from, so two reminders. One is from pre-calculus, or to be more accurate, two equivalent identities from pre-calculus or from trigonometry, and two derivative formulas from Calc 1. So from pre-calculus, just as a reminder, secant squared of x is equal to 1 plus tan squared of x. In this lesson, sometimes we need this. And also, if I subtract 1 from both sides, what I will get is tan squared of x is secant squared of x minus 1. These two are obviously equivalent. The other reminder that I want to make from the derivatives in Calc 1 is the derivative of tangent of x is secant squared of x, and also the derivative of secant of x is equal to tan x times secant x. So these are two reminders that will be very helpful in the lesson that we have today. So the integrals that we are investigating are the integrals of this form. Integral of tangent to some integer times secant to some integer, and you want to find these integrals. And as I mentioned, what we'll discuss will be two cases. Case 1 is when the exponent of secant, or n, is even. Meaning that I deal with the case that tangent to the power of m, secant to the power of n, and this n is even. So what should we do for this situation? Let me write a brief note, and then we'll do an example to clarify that. So the power of n is, the power n for secant is even. In this situation, separate secant squared and write it next to dx. And then use the substitution u equals tangent of x. This is a very brief note. It might look a little bit confusing until we do an example to see how it works. So I want to find the integral of tangent squared of x secant to the 4 of x dx. This is an example of case 1 because this power of secant is even. Remember that case 1 for this kind of integrals is when the exponent of secant is even. And here is the case. According to that note, to solve this, we separate secant squared and write it next to dx. So it is secant to the 4. So when I separate secant squared from that, I will have secant squared, secant squared. So from secant to the 4, I separated secant squared and write it next to dx. So the remaining secant will have power 2. Then we use the substitution. Let me write the substitution here. According to this note, we use the substitution u equals tangent of x. So u is tan x. By that reminder that we had from Calc 1, the derivative of tangent is secant squared. So du over dx is secant squared of x. And in other words, du is secant squared of x dx. So what do we have now? U is tan x, so this is going to be u squared. Remember that u is tan x, so this is u squared. Du is secant squared dx. Therefore, this part is going to be du. But there is one thing that needs to be written in terms of u, and that's secant squared. Do you remember that I just mentioned a reminder from pre-calculus that secant squared, the very first identity here, secant squared is 1 plus tan squared. So this secant squared here is 1 plus tan squared. But tan is what? Is u. So it is 1 plus u squared. So this secant squared is going to be 1 plus u squared. So let me just write 1 plus u squared. Because u is tangent of x. So this becomes 1 plus u squared. Obviously, I'm dealing with this integral u squared times 1 plus u squared du. That's quite simple because first I distribute u squared over that parentheses. So u squared times 1 is u squared. U squared times u squared is u to the 4. Antiderivative of u squared is u cubed over 3. And antiderivative of u to the 4 is u to the 5 over 5. And then plus c. But last step, as we have done with all the indefinite integrals that we use substitution, we do a back substitution. U is tangent of x, so u cubed is tan cubed of x, and there is over 3 here, plus tan to the 5 of x over 5, and then plus c. Okay, let's do another example. Let me write it down here. I want to do the integral of secant to the 6 of x dx. We don't see tangent, which means the power of tangent is 0, but secant is to the power of 6. And in case 1, the exponent of secant is an even number, and 6 is an even number. So what we should do is, as I explained in the note, we separate one copy of one secant squared from secant to the 6 and write it to dx. So secant squared was separated from secant to the 6 and was written next to dx. So what's left over is secant to the 4. But as you might remember, in this case, u is tan x and du is secant squared of x dx. So obviously this is du. But here is a little bit tricky. We don't see tangent, and I want u be tangent of x. But we know that from those reminders, secant squared is 1 plus tan squared. But here I have secant to the 4. Secant to the 4, in fact, is secant squared of x squared. And secant squared is 1 plus tan squared. So this is 1 plus tan squared. And u is tangent of x. In other words, that tan squared is u squared. So in fact, we are dealing with this integral. The integral of 1 plus u squared all squared du. One plus u squared all squared. How do we expand that? We remember a plus b squared is a squared plus 2ab plus b squared. So if I do the same thing for 1 plus u squared all squared is going to be 1 plus 2u squared plus u to the 4. Antiderivative of 1 is u plus 2 times antiderivative of u squared is u cubed over 3. U cubed over 3, or I can write it here, 2/3 u cubed. That 2 is from here. That 2 is the same 2 here. And antiderivative of u to the 4 is u to the 5 over 5 plus c. Just a back substitution, u is tan x, so the final answer that I want to type in this box, tan x plus 2/3 tan cubed x plus tan to the 5 of x over 5 and then plus c. So in case 1 that we investigated there was a condition on the exponent of secant and n was even. And when n is even, that's how we deal with the integral, as I wrote down in this note, and we applied to these two examples. We have another case that we study here, and that is condition of on the exponent of tangent. So case 2 is not a condition on n, but on m. And that is m, the exponent of tangent, is odd. It's an odd number. So in the integral of tangent to the power of m, secant to the power of n, this m is an odd number. Odd number like 1, 3, 5, 7, and so on and so forth. So let's have a note for this case. In this case, we separate tangent times secant and write it next to the x. Can you guess what substitution we use? Use the substitution u equals secant of x. Let's do an example. Integral of tangent to the power of 3 of x secant to the power of 9 dx. The power of tangent here is 3, is an odd number, so this falls under case 2. So I separate one copy of tangent, one copy of secant, in other words, the product of tangent and secant, and write it next to dx. So tan x, secant x, I write it next to dx. From tan cubed, one tangent was used for this purpose, so tan squared is remaining. From secant to the 9, one secant was used, so secant to the 8 is remaining. Remember that in case 2, u is secant of x. I made the remainder. I'm sorry. I mentioned before that the derivative of u with respect to x is tan x secant x. In other words, du is tan x secant x dx. So that's why this is du. And that's why we separated tangent and secant and wrote it next to the x. U is secant, so this is going to be u to the 8. How about tan squared in terms of secant? Again, let me remind you that over here, tan squared is secant squared minus 1. So in fact, this is secant squared minus 1, and the substitution was u equals secant of x. In other words, this is going to be u squared minus 1. So let's see what we have so far. U squared minus 1 times u to the 8 du. We distribute u to the 8 over the parentheses. U to the 8 times u squared is u to the 10. Then minus u to the 8 times 1 is u to the 8 du. Antiderivative of u to the 10 is going to be u to the 11 over 11. Antiderivative of u to the 8 is u to the 9 over 9, and then plus c. And then just a back substitution because I need to write everything in terms of the original variable. So the final answer is going to be, knowing that u is secant of x, so secant 11 of x over 11 minus secant to the power of 9 over 9, and then plus c. Let's do another example. Please try this on your own before you watch the solution here. The integral of tangent to the 5x secant x dx. The exponent of tangent is an odd number. That's case 2. That is the exponent or the power of tangent is 5, is an odd number. So we should use the substitution u equals a secant x, and as we have seen before, du is tan x secant x dx. Remember that for this situation, we separate tangent times secant and write it next to dx. So this is going to be tangent to the 4x tan x secant x dx. Why it became tangent to the 4? Because I wrote tangent times secant next to dx. So one tangent is gone. So from tangent to the 5, tangent to the 4 is remaining. So this is du. But u is secant of x. How can I write tangent to the 4 in terms of secant of x? Remember that over here, tan squared is secant squared minus 1. Let's see how we can use that. So tangent to the 4 is tangent squared all squared. And tan squared is secant squared minus 1. So I can replace that by secant squared minus 1. And the substitution tells us that u is secant of x. So that secant squared becomes u squared, and then minus 1. So let's see what we have so far. U squared minus 1 all squared du. Using algebra, we know how to expand u squared minus 1 squared, which is going to be u to the 4 minus 2u squared plus 1. Antiderivative of u to the 4 is u to the 5 over 5. 2 times u squared. Antiderivative of u squared is u cubed over 3. So this becomes 2/3 u to the power of 3. And antiderivative of 1 is u. At the end plus c because it's an indefinite integral. So the final answer, which is obtained by back substitution, is going to be secant to the 5 of x over 5 minus 2/3 secant cubed of x plus secant of x, and don't forget plus c at the end because it's an indefinite integral. You might have noticed that case 1 and case 2 sometimes might have an overlapping, because in case 1 we had a condition on the exponent of secant. In case 2 we had a condition on the exponent of tangent. Sometimes we have an overlapping. So there are some examples that belong to both cases. So we have two options to solve those problems. So let me write a note. Some examples, of course, not all the examples, but some examples belong to both case 1 and case 2. We can use either of these two cases or the way that we did these problems and find the answer. However, the answers of when we follow the method for case 1 for this kind of examples will be a little bit different from the answer we get from case 2, but they are equivalents. They look different, but they are equivalent. They are not totally different answers, though these answers are equal to each other. So let me give an example that belongs to both case 1 and case 2. So we have two options. You can choose either one. The integral of tangent cubed of x secant to the 4x dx. This belongs to case 1 because case 1 was saying that the exponent of secant is even. 4 is even, and so it belongs to case 1. It also belongs to case 2 because case 2 was saying that the exponent of tangent is an odd number and 3 is an odd number. So we have two options. Either one is fine, but let me do both. We can see. So for this example, we have two options. Of course, for many examples, we don't have these two options. But for this one, we have two options because it has both the condition of case 1 and case 2. So if I go with u equals tan x, and therefore du is secant squared of x dx. If I go with this, what I get is that integral will be equal to, so this integral is equal to, so we separate one copy of secant squared. So secant squared is separated and written next to the x. So from secant to the 4th, secant squared is remaining, and I have tan cubed. Secant squared dx is du. U is tan of x, so this is going to be u cubed. What about this? Secant squared is 1 plus tan squared, so it's going to be 1 plus u squared. So I will have the integral of u cubed times 1 plus u squared du. If I distribute u cubed over the parentheses, it's going to be u cubed plus u to the 5 du. Antiderivative of u cubed is u to the 4 over 4. Antiderivative of u to the 5 is u to the 6 over 6 plus c. And u is tan x, so it's going to be tangent to the 4x over 4 plus tangent to the 6x over 6 and then plus c. As I mentioned, for this example, we had another option. Let's try that as well. I use a different color. So it also belongs to case 2, so I can let u be secant of x, and du is tan x secant x dx. Okay. So this integral will be equal to, I separate one tangent and one secant next to write it next to dx. So it's going to be tan x secant x dx. So from tangent cube, tan squared is remaining. From secant to the 4, secant cube is remaining. This is u cubed. This is du because in this situation, u is secant. So secant cube is u cubed, and tan x secant x dx is du. What about tan squared? You know that tan squared is secant squared minus 1, and u is secant of x. So this is going to be u squared minus 1. Again, why is it u squared minus 1? Because tan squared is, by the reminder that we had from pre-calculus, is secant squared minus 1. And the substitution is u equals secant of x. That's why it becomes u squared minus 1. So let's see what we have so far. U squared, integral of u squared minus 1 times u cubed du. Distribute u cubed over the parentheses, so you will have u to the 5 minus u cubed du. Antiderivative of u to the 5 is u to the 6 over 6. Antiderivative of u cubed is u to the 4 over 4, and at the end plus c. By back substitution, u is secant of x, so secant to the 6 over 6 minus secant to the 4 over 4, and at the end plus c. Although these two final answers, one of them in terms of tangent, one of them in terms of secant, they look different, but they are equivalent. So for this example, we had two options because it belongs to both case 1 and case 2. But for some examples, it only belongs to case 1 or only belongs to case 2.